Now we're ready to introduce the Newton's second law method to analyze rigid body motion. Okay? Now we take any random rigid body shape. Okay? Now this rigid body might be subject to multiple forces, okay, in any random direction. Okay? And let's say F1, F2, and F3, and this point G is the center of gravity. Now some of the forces might be going through the center of gravity, for example, weight. Also, this rigid body might be subject to a couple. Okay? You might remember from statics. Okay? The couple is the effect of two parallel forces, okay, acting at a distance apart, okay, going at the opposite direction. Okay? So this couple right here, okay, these two forces, okay, create something called couple. Okay? So these two forces would tend to create, okay, or give an extra rotational, okay, motion. Okay? So it will result in an extra rotational motion, okay, to this rigid body. So you draw this free body diagram, okay, that includes all the forces as well as applied couple. Okay, so this M1 right here is applied. Okay, and these forces are external forces, including applied forces. Let's say you actually push this object, okay, or weight, okay, is also external force. Okay. Friction is also external force. Right? So, in the free body diagram, you include all these external forces and moment. Okay? And then you draw a kinetic diagram that includes the result of the motion. Okay? And you draw two things. First, the linear portion of the acceleration, which is the ma term. Okay, so mass times acceleration through the center of gravity. So ma(g). And the second, you draw the rotational acceleration, which is the I alpha term. So the mass moment inertia, that's where it comes in, okay, times the angular acceleration alpha of this rigid body. Okay? So now you write down two equations. Okay, so under the Newton's second law method, there's a second law equation, okay, and that should be very familiar, and that applies to the linear portion. Okay, so sum of all the forces, right, equals mass times acceleration through the center of gravity. Okay, so that is pretty straightforward. Now, this part right here, the second equation, is something we need to pay attention to. Okay? So this says sum of all the moments about some point. Okay? In this case, I'm gonna say that it's some moment about point G. Okay, just for simplicity. Okay? So some moment about point G equals I alpha. So mass moment inertia about point G, okay, about the center of gravity, times angular acceleration. That's all. Okay. So this second equation is like the rotational counterpart to the Newton's second law. Okay. What's moment? Well, moment is simply applied couple as well as any rotational, okay, forces. Okay. The rotational effect from these linear forces. Okay. And it's simply force times distance between them. The shortest distance between this point G, and this force. Okay. So now, if this rigid body is rotating about some point other than the center of gravity, let's say point O, then what should we do with this? Okay. So this equation right here, okay, is for the case where this rigid body is rotating about point G, center of gravity, right? And then it's just straightforward, fine and dandy. If it were to rotate about point O, okay, now this point O may or may not be on the rigid body itself. Now this point O can be outside of it. Okay, so this whole thing may be rotating about that point. Okay, so in that case, which is very common, okay, in real life, you need to modify this equation so that subscript now becomes point O, and then the right hand side is just simply mass moment inertia about that same point O. That's all. Okay, so this subscript, okay, can be anything, okay, as long as it's consistent, right? Some moment about point O equals mass moment inertia about point O times the angular acceleration, okay, of the rigid body. That's all. Okay. So in applying this sum of moment equation, you always need to define the positive direction, okay, whether it's clockwise or counterclockwise. It's up to you. Okay. Now applying this now to this picture right here, where my point O is, I chose to be this location. Okay. So let's expand it. Left hand side, sum of moment, okay, with all these given forces and a flat couple. So left hand side becomes the first term, M1 applied couple, okay, simple as that. Second term is F1, okay, this applied force times R1, where R1 is the shortest distance between this force and point O. So I'm going to draw an extension to this line of action of F1, and the distance, the shortest distance between point O and this line of action is simply the perpendicular distance. Okay, so this is my R1. So F1 times R1. So F1 going this way times R1. R1 is also known as the moment arm. Okay? So you multiply F1 by this moment arm, it will give you the moment created by F1 about point O. Okay? Next, for F2, so it's simply F2 times R2. And notice that there's a negative sign right here because F2 is pointing down this way, okay? And the moment created by F2 about point O is counterclockwise, which is opposite of my positive direction. Okay? And the distance between these, the F2 line of action and point O, again, is the perpendicular distance. So let me draw something like this, perpendicular. That's my R2. Same thing, keep going for F3. F3 going this way, so I'm going to extend this line of action, F3, and find the shortest distance between them, and that's my R3. Okay, so again, it's negative sign because F3 about this point O will create a negative moment, counterclockwise moment. So again, it's a negative sign. So F3 times R3. And that's it. That's all left hand side. Okay? So as long as you take into account all the applied couple as well as the moment created by all the applied forces, the external forces, that's all your left hand side.